Besides shortcutting long division, synthetic division offers us something else that's pretty useful. Via the remainder theorem, we have this statement here that says that if you have a polynomial f of x, then if you're evaluating f of r, so f of r equals the remainder when f of x is divided by x minus r. So in plain English, to kind of translate that for us, whatever our divisor is, r, think of that as the input, as the number you're plugging into the function, and whatever the remainder is, that's the output. So, for example, if we look at the example here, so we want to find what f of negative 2 is for this function f of x. So what I would have to do is I'd have to plug in negative 2 in for x, where I see it here, here, here. I'd have to raise it to the fourth power, multiply by 4, raise it to the third power, multiply by 16, raise it to the second power, multiply by 7, and then add and subtract all those numbers together. Instead, we could use synthetic division. And I think we're going to see that that's going to be a little bit easier than having to go through what I just described. So if I set up my synthetic division box, my divisor is going to be the input number here. So that's going to be negative 2. And then inside the box are going to be the coefficients of our polynomial here. So we're going to have 4, negative 16, 7. Now notice the x term is missing, so I do need to have a placeholder for that. And then 20. So if we extend this a little bit here, and so now we can go ahead and do our synthetic division. So I bring down the 4 to get us started, and then we multiply on the diagonal. Negative 2 times 4 is negative 8. Add in the vertical direction. Negative 16 plus negative 8 gives us negative 24. Multiply on the diagonal. Negative 2 times negative 24 is 48. Add in the vertical. 55. Multiply on the diagonal. Negative 2 times 55 is negative 110. Add in the vertical direction, so I'm just going to get 0 plus negative 110 is negative 110. And we have one more multiplication. Negative 2 times negative 210, or negative 110 gives us 220. And then we add in the vertical direction, 20 plus 220, 240. So remember, that last number is our remainder. And so what we have found is that when we plug negative 2 into this function, our output is 240. And so I would argue that that's a lot easier way to get to that answer than, like I said before, raise negative 2 to the fourth power and then multiply by 4. And then raise negative 2 to the third power, multiply it by negative 16. So on and so on to get to that same result. So while it may be debatable whether using synthetic division or just plugging in negative 2 everywhere is easier to figure out what f of negative 2 is, we're going to see that there's no doubt that it's much easier to use synthetic division to find f of 1/2, to find the output when you plug 1/2 in. Because again, if I had to plug in 1/2 for x everywhere, I'd have to raise it to the fourth power, I'd have 1/16 times 4, I'd have all these fractions I'd have to carry through the problem. Instead, if we set up our synthetic division with 1/2 as the number on the outside here, and then we use our coefficients, 4, negative 16, 7, don't forget the 0 placeholder for the x, and 20, now we can roll through it by bringing the 4 down, multiply on the diagonal here, so half of 4 is 2, negative 16 and 2 is going to be negative 14, half of negative 14 is negative 7, add in the vertical direction, we get negative 7 plus 7 is 0, half of 0 is 0, 0 plus 0 is 0, half of 0 is 0, and then 20 plus 0, we get 20. So the output when 1/2 is the input into this function is 20. And so I would argue that this is a much faster way to get this result using this concept of the remainder theorem, that whatever your divisor is as your input, whatever your remainder is as your output, is a much better way to get the answer than to actually take 1/2 and plug it in for x everywhere in this function. There are times where that's faster, just plugging the number in is faster, but this is certainly a case where this remainder theorem becomes a very handy tool. And related to the remainder theorem is something called the factor theorem, which basically just says if you try some synthetic division and you divide by r and you get a remainder of 0, that means that x minus r is a factor of that polynomial. So if you divide and you get a remainder of 0, x minus whatever you divided by is a factor. So how can we use this? Well, in the example that we have here, we're given a polynomial function, and we're told that -6 is a 0. We're asked to confirm that, and then we want to find what the remaining zeros are. So what I'm going to do is I'm going to set up my synthetic division to verify that -6 is a 0. So the way I'm going to do that is to hopefully get a remainder of 0 when I'm done. So I've got the -6 on the outside, and so I need the coefficients of my polynomial on the inside. So I've got 1. Now notice the x squared term is missing, so I need a placeholder 0, then -52, and then -96. So we go through our synthetic division. I just bring down that 1. -6 times 1 is -6. Add in the vertical direction. -6 times -6 is 36. Again, add in the vertical direction. We get -16. -6 times -16 is indeed positive 96. So we have confirmed that -6 is a 0. So that means we can rewrite our function as f of x equals, instead of writing it as it was originally, I can write it as x minus -6 or x plus 6, since I've confirmed that that is a factor of our polynomial, times, and then I'm going to use the answer here as the thing that I would multiply x plus 6 by to get back to my original function. So that's going to be x squared minus 6x minus 16. And so then to find the remaining zeros, I need to factor this guy. I need to set this equal to 0 and solve. So we break it up into our two sets of parentheses, x and x. Hopefully we know that it's going to be one positive and one negative. So we're looking for two numbers that multiply to make 16, but have a difference of 6, with the negative number being larger. So I'm going to have a -8 and a +2. And so then if I set those two factors equal to 0, to go along with the -6 that was given to us, my remaining zeros are going to be -2 and +8. So via the factor theorem, we confirmed that -6 was a 0 by getting a remainder of 0 in synthetic division. We then rewrote -6 in factor form of x minus -6, so x plus 6, times the answer that we got over here. And so we knew that these two expressions here would remultiply to make our original, and so then we just had to solve for the remaining zeros by setting that x squared minus 6x minus 16 equal to 0. So we can try that one more time. Similar question. We want to confirm that 1/2 is a 0 of this function, and then we want to find the remaining zeros. So I go to my synthetic division. I'm going to have a 1/2 on the outside here. I'm going to use my coefficients of the polynomial. This time none of them are missing. So I've got 2, -15, 27, and -10. And so then I can start by bringing down the 2, and then we multiply. 1/2 times 2 is 1. -15 plus 1 is -14. Half of that is -7. 27 and -7 is 20. Half of 20 is 10. And so -10 plus 10, I get 0. So I have indeed confirmed that 1/2 is a 0. So that means I can rewrite this function. Let's try that again. As f of x equals, so then the first factor is going to be x minus the 0, so x minus 1/2, times the results of my division. So remember, this was the coefficient in front of x cubed, so that means this 2 down here is going to be the coefficient in front of x squared. We always go down by one exponent. So we've got 2x squared minus 14x and then plus 20. So I need to solve this quadratic by setting it equal to 0 to find the remaining zeros of this polynomial function. So the first thing I'm going to do is divide everything by 2 in this problem, just so that my numbers are a little bit easier to work with. So I end up with x squared minus 7x and then plus 10 equals 0. So hopefully we can see that this is indeed factorable. I'm going to have x as the first piece in each set of parentheses. I need to multiply to make a positive, but add to make a negative. So I need 2 negatives. And so then my factor pair that multiplies to make 10 but adds to make 7 is going to be 5 and 2. So to go along with the 1/2 that was given to us, we've got zeros of 5 and 2. So there are the 3 zeros of this function.